sitting having a conversation there, and I'm supposed to be talking. So, for those who came to see Fahim, you've got me for the first 10 minutes, and my job is to talk for 10 minutes and then get off, so Fahim can actually say his piece. So this is Fahim's PhD student working on this project under the supervision of myself and Anne Twaler. And very much what we're doing is really, many of you will be aware, there's been quite a lot of activity in the simulation community over the last few years around the topic of conceptual modelling. And actually one thing that's been identified is that we've really taken very little notice of the world of computer science and the various sub-disciplines within that in terms of the input that they could bring to the simulation community. We've very much grown in our own separate ways in terms of talking about conceptual modelling. And if you look at the computer science literature, you will find quite a lot of stuff around the topic of conceptual modelling. So what this study really is about is how do we bring the lessons from computer science into the world of particularly discrete event simulation. And actually what we're discovering is that actually that is not that straightforward because there are quite a few differences in the way that we think. So what I'm going to do basically is I'm going to sort of give the discrete event simulation view of the world and sort of introduce our thinking, and then Fahim's going to come and do two things really. First of all, talk about some of the differences within and between computer science and simulation, and then also just give some thoughts on a couple of ideas that we could bring across to help us with the conceptual modelling activity for simulation. So if we look at the discrete event simulation world, there are many perspectives. In fact, the talk session I was in this morning commented on that already somebody had identified at this conference. The word conceptual, or words conceptual modelling have been used in a number of ways to mean, in many ways, quite different things. So we have to be very aware of that. What sort of things are we, and actually, yeah, reasonably agreed about, is that conceptual modelling is about communicating the model. In fact, here I think that's just an example in that respect of communicating an agent-based model using some UML diagrams, an example of that sort of communicative model. A conceptual model is something that sits in the mind of the modeler, and then we try and communicate. It's not about the software we're going to use, so it's not software specific, but it's about the concept of the model. It's about determining what the model's going to cover, and it's actually a basis on which we can lead to model validation. And if you look in the simulation literature, there's very much sort of those are the kind of themes that are coming out of it. Of course, the best way of thinking about conceptual modelling is my own approach, but I'm biased. And I would make it very clear that there are those who would disagree with what I'm about to show you. So, and I think that's a healthy thing, that we have a range of views as to what conceptual modelling is about, and a healthy debate about this. Some of you will be aware that a group of four of us edited a book on this in 2010, and we deliberately made no attempt whatsoever to come up with a unified view, because there are 18 chapters in that book, and between them are a range of different views. And I think that's a good thing, that we actually, in an evolving debate around conceptual modelling. Anyway, this is the way that I tend to try and express what I see as being conceptual modelling for discrete event simulation, and perhaps more broadly in the world of OR, is that when we're faced with a problem that we're aiming or is amenable for simulation, then we start in a problem domain where there is a real world in which there sits a problem. And the first job, really, of a modeller is to actually acquire knowledge about that real world. So it's about actually acquiring knowledge from the real world, eliciting that knowledge to come up with a system description, a way of describing that world. And the point here is we're moving from a very much a world that's not well known to a very nice, neat description of that world as best as we know it. In that process of acquiring knowledge about the world, there will be things we need to know about, but we don't actually know anything about. So the way we fill those gaps in our knowledge is to make assumptions about the real world. So we come up with a set of assumptions that we're making. Now, can I be clear here? First of all, I did say this is the first thing we do, but these arrows I'm about to put up are by no means meant to be a sequencing. They're about information flows. So this is an iterative process that goes on throughout a simulation study, backwards and forwards stepping, acquiring more and more knowledge. So it's not about necessarily, I get all the knowledge and then I build a simulation model. And the other thing to say is the system description may well never be written down. So this could be in the mind of the modeler. It's acquired knowledge that the modeler gains about the real world. They may never actually communicate that in any concrete form. It may simply be an artifact that remains within their minds. And this actually, if you read, and Fahim will bring this out in a minute, if you read the computer science literature, what I'm calling a system description will be called a conceptual model. And that's going to cause some confusion when we're comparing the two fields. And my argument for not calling that a conceptual model is this, is that actually once we've acquired knowledge about a system, the next flow of information is about how we then decide to model that system as best as we understand it. And to me, that is the concept of the simulation that I'm going to build, and therefore the conceptual model. It's how I conceive the model that I'm going to develop in some simulation software. And the point now, as I move from the problem domain to the model domain, is what I'm starting now to do is to abstract from the real world to a conceptual model. And this is actually, I think, where we do have quite a difference, to me anyway, in the simulation world from perhaps the computer science world, is model abstraction is a key element of what we're trying to say. And my point always is, and the reason I use this diagram is actually the biggest issue, I think, in bad simulation modelling is people acquire a system description and then they model it. And they never abstract. And the next thing I'll do is just a very brief example just to try and illustrate how, what I mean by abstraction. And the process of abstraction is about deliberately simplifying the real world, our understanding of the real world, to come up with a simpler model. And so we, at this point, have the idea of generating simplifications. And note here, assumptions and simplifications are quite separate. Assumptions are filling in gaps of our knowledge of the real world. Simplifications are deliberate modelling choices to model the world more simply. And they are quite different in that respect. So that is our conceptual model. If I just fill out the rest of this, and we're not going to talk about this here really, is we then design how we're going to code this. We then code it into a computer model, and by code I'm using that in the very broadest sense of the word. Anything from using Excel through to a simulation package to actually using coding language. And that computer model then becomes our simplified representation of the real world. So by conceptual modelling, we're really referring to this process of knowledge acquisition and model abstraction, including the generation of assumptions and simplifications along the way. So just very briefly, because my 10 minutes is nearly up, and I need to give Fahim some time. Some of you will have seen this example before, but I use it to try and demonstrate this idea of model abstraction. This is a few years ago. We were involved with a hospital in Birmingham, in fact, that was building a new outpatients building, and they wanted to know how many consultation rooms they needed in that new building that they were going to create. And it was a multi-million pound project. Dollars here, because we've taken it from an American publication. We were spending pounds in the UK. And actually, if you start to look at this sort of system, it really actually can be quite complex in terms of different clinics, different patient types, arrival times, etc., etc. And we didn't actually, A, have very long to spend on this, and B, they had to make a decision within a couple of weeks in the number of rooms. So it wasn't a case of we were going to go away and build a full model of everything we knew about that system. So what we did was what I would call a far abstraction. We abstracted a long way from the real system and came up with a model that was basically a very, very simple multi-server single queue problem. So patients arrive, and we just had some basic data around number of patients that arrived for each clinic. We took the busiest day of the week, which is Monday morning. We knocked a few off because we know a few don't attend each time. We had some data on that. We bung them into a waiting area, and then we actually see them through a consultation process. Key simplification was we actually threw all the patients for that clinic in at 9 o'clock in the morning. Now that is completely wrong in terms of the real world, because they're scheduled to arrive at a particular time. But the reason that was a satisfactory simplification in this case is we were not trying to measure waiting time. What we wanted to know was when was it that the last patient would leave this clinic. So we didn't actually, all we wanted to do is make them all available, and then we just ran them through, and we just simply, the one data point we took out was when did the last patient leave this particular clinic. Now, okay, time's quite limited, but just to give you a sense that, of course, that looks nothing like an outpatient's building. It's an extremely simple model, but it took us a day to build it and run it and come up with some results. And that's the key point, is we were able, through a process of far abstraction, to come up with a very simple model. Just for interest, the results look something like this. So they started off with a plan to have 40 rooms, and this, we ran the model 1,000 times, 1,000 replications. Some talks this morning about parallel processing. We didn't need any of that because this model ran in seconds, because it was a very simple model. Another benefit of simple models. Obviously, if it's more complex, and that's the sort of thing we need to move to. And what we find out is, they wanted to kick everybody out by, after they start at 9, they want to kick everybody out at midday, so they can go and get their lunch before they start the afternoon clinic. So in something roughly over half of the runs here, we're breaching that limit. So 40 rooms is not sufficient in this case. So what we then did was increase the number of rooms, and if you're going towards 50 or 60, then what you're going to find is you're going to actually manage to get the patients out, in most cases, within 3 hours. Now that in no way is a predictive model. It's too simple, and there's lots of things that aren't in that model that will make the situation actually worse. So my argument is that is a lower bound on the number of rooms that you need, but what we were able to do is very quickly and simply give them a result that was beneficial in helping with their decision process. I'm going to shut up, and I'm going to hand over to Fahim, who's going to tell you something much more interesting. There you go.
Thank you very much, Stewart. So the purpose of the study, what we took, Stewart, me, and Drilla, basically we started with comparing the field of the computer science with conceptual modeling. So just to let you know that we really focused on this word, conceptual modeling. Right? So we wanted to know what people are doing in computer science and how can we compare it in modeling and simulation. The 4 components that we looked at primarily were the definition of the conceptual model, the purpose, the process, and the testing. So I will explain briefly about how we went on. If we subdivide the field of the computer science, we see 3 major divisions in that area. Recently, I mean not say recently, but software engineering is now treated as a separate discipline. So it can be a sub-discipline of computer science. Previously, they were like kind of merged. Information system, databases, and software engineering, those 3 areas basically we looked at. So we start with the definition. When we look at the definition of the conceptual model, what we see that mostly, in the bracket I have put up the abbreviations for like databases, information systems, and software engineering. And here the component which was mostly prominent in that areas I've listed. So for example, if you see in database information system, it is usually the definition is really a formal document or a process, right? If you look in all 4 fields, the common thing is it was considered a model of the real world, right? So you have a problem, you have a model, which is not really a design, but it is just the idea of what your real world looks like that. Now, in some cases, it is also considered a model of a proposed system. So what you need to model, it is a proposed model. But that is common mostly in software engineering and modeling and simulation. What we see in modeling and simulation specifically is that it is mostly considered as an informal activity or a kind of a mental model or documentation. So that's kind of a difference which we see. When we come to the purpose, basically all communities agree upon understanding and communication element that, yeah, this is the purpose of doing a conceptual model. Again, one of the things that is common in software engineering and modeling and simulation was the abstraction principle, which Stewart has just stated about. And that we find, we really see that this is some kind of thing which software engineering also does. If we come to a modeling and simulation thing, basically what what is common was, of course, abstraction is there and some understanding, which is considered to be the purpose of the conceptual modeling. Now, this is a bit detailed, but I'll just quickly just tell you that process of the conceptual modeling is considered very theoretical in computer science. They are using philosophies from ontology, cognition, linguistics. They have those frameworks, whole lot of literatures on that from Wand and Weber. There's quite a lot of things around there, but this is a kind of a summary. They use modeling languages to do the process, which most commonly they use ER models and they use UML, which is also used at some extent in modeling and simulation, not the ER models, but the UML, just like Pierre said. Then they're also using formal methods to do this conceptual modeling, which can be composed of software engineering methods, software requirements engineering specifically, and some formal methods. Well, in modeling and simulation, we don't have any that kind of a structured framework. We do have some interesting works, but they are mostly descriptive or informal in nature. And almost the same thing happens in the testing. How do you evaluate the conceptual model? So in computer science, they have like formal approaches to test their conceptual model. They use some kind of ISO standards, like in database and software engineering, there are well-defined standards based on ISO, and they use those to test and evaluate the conceptual model. But with modeling and simulation, there are only general criteria, mostly guidelines about how to evaluate the conceptual model. Now, okay, I don't want you to read it, it's there in the paper, but the thing is, this is a kind of a matrix summary which we made. And we placed the components and we placed all the 4 fields, and we listed the key results here, so that we can compare if we want to see software engineering objectives compare with the other 3 fields, so we can easily see what's actually the findings are. So it's just to how did we basically illustrated the results. But the key analysis when we did, and we come to a point that there is some definition, of course, when it comes to definitions and purpose. So there's not really that much problem within modeling and simulation and the computer science. But when it comes to the process and when it comes to testing, modeling and simulation really lack in most of the like guided and theoretical and formal approaches. We don't see those much. And the process and the testing frameworks on those kind of approaches from computer science is really a need for the modeling and simulation community. So what we did, we considered some methods from software engineering, software requirements engineering specifically, because we believe that software requirements engineering is basically close to the kind of abstraction thing in the modeling and simulation. Now this is a method. I will not go into the details of the method, but I'll just give you a brief idea of how this method works. Preview is one of the methods that is a viewpoint-oriented approach in software engineering. In software requirements engineering, they have goal-oriented methods, they have like scenario-oriented methods, they have ethnographical approaches, and they have viewpoint-oriented methods. So many methods are around. We did take one of the methods, it's called preview from Somerville, and basically the problem is centered around here. For example, in this case, it was a telephone booking system. And then all the viewpoints basically are generated on that problem. Now when I say viewpoints, it means how many people, either it can be person, there can be any role, any organization, any subsystem or external system or any policy or standard that basically puts some constraint on the problem. So that is how they create those kind of views on the same problem from different perspectives. And one of the good thing about this is that all viewpoints will have some stake in the system. So whether it's a customer sales representative, it's a service level information, even if it is a passive component, but someone talked about passive and active component, but they would have some stake in the problem. So they will be generating some requirements or some conflict. In the original preview method, then they create a viewpoint template. For each of the viewpoint, they create this kind of a template, and they record the information like requirements and what is the concern and what is the focus of the viewpoint. For example, if it is a train, in the same case, if it is from the customer viewpoint, he wants it really early, all the response and all the booking. From a security point of view, you may need to validate the call. So these two viewpoints can conflict on the requirement, then the analysis phase can be done to see which viewpoint requirement has got the priority. So this is how it is performed. What we did, we added some fields from the modeling context into the every viewpoint. And primarily what it was, basically the details and the experimental factors and the outputs that each viewpoint was basically had the information about this. And we put it combinedly with the viewpoint template. We did a couple of test cases on generating the viewpoints. We got some very good results. We did the system description. No point to go into that details, but yeah, we did all that. But what we realized, the good news was it did not work. And the thing is, when we say it did not work, was because not it completely failed. What happened? We realized that it is good for structuring different views of the system, and we got a good description about the whole problem. We got some different viewpoints. But it was again lacking in some structure. And when I say lacking in the structure, it means that it was still a bit of descriptive information that we need to analyze when it comes to abstraction again. And then abstraction was again not delivered effectively. When it again, if I continue with the first two slides, we generate the system description, but when it went to abstraction, we had to do some intuition and we do some like a descriptive analysis to say, okay, these viewpoints are not relevant, so we are not dealing with it and things like that. But it was not, we felt that it is something lacking here. But it was not failed completely, but we thought that maybe a different approach would be better. But then very briefly, because it's just the recent work we did, I come up with another design technique, which is again a software engineering requirements, software engineering method, but it is heavily used in the software requirements engineering. And to just give you, there's only one slide on that because the details are ongoing, so we didn't put up it here. But it's a kind of a notation. It's a very we believe that it was a notation which was very beneficial for the discrete events kind of a domain. So we adopted that structure analysis design technique. The original block looks like you put an activity in between, and then you have 4 arrows defining input, output, control, and mechanism. And they use it quite heavily in software engineering, where they use hierarchical decomposition of the requirements, and they have like a higher level of the process, and then they put this information there, and then they keep decomposing those levels into further lower level details. So quite a lot of heavy details on that. What we did, we basically modified this original SADT into a little bit more about centered on the activity, where we thought that this activity is our main activity, and it can be combined with some of the control and the resources. The mechanism will be the resources in the individual component of DES. The control will be the same because it is any requirement constrained on that activity, and then input-output activity. We attached one extra level of entity on the output arrow. The good thing about this representation was, on the single unit, it contained all the information that was required by a single transition. Input, output, resource, control, everything is in there. And we just feel that, yes, it's a kind of a thing which we can use to create diagrams from a bottom-up approach, where you can create those local diagrams separately, and then from there onwards. Now there's a process involved which I cannot explain here, but you can come up with a high level but more detailed diagram of the whole process. So yes, and it did work actually with those test cases, and we got some good results. But of course, we need to really look more forward into development. We are done with the development almost, but we need to see how abstraction is dealt more effectively, and then some modifications, and then comparisons with the other frameworks. Of course, this needs to be validated. So yes, it's all going. Thank you. Thank you.
We have some questions.
Are you going to go talk to any software engineers, things about how they do that conceptual modelling? I worked as a software engineer, and my impression was that they don't really do that sort of stuff, and a lot of it's in their head, and they'll just code, and then at the end we'll put together some pictures and some UML to describe the software?
The thing is, they may not call it software conceptual model, but what do? They definitely are doing software requirements engineering. They call it like that. And if it is a heavy project, it's an expensive project, they definitely want to involve some formal approaches and formal methods to do that. But as I said, there are differences about how people look at conceptual model. So you are right that they say that thing, but still they are drawing some diagrams, still they are analyzing the requirements. That's why we feel that this software requirements engineering phase is more close to conceptual modeling in MNS, modeling and simulation. But still, yes, because we studied the literature, and in the literature there are a lot of debate on conceptual modeling, even from the computer science people. The one I listed here and the all in my paper. There are people from computer science. They do talk about conceptual modeling, but their view of the conceptual model may be different, because majority of them just see a conceptual model about way of representing the problem domain in diagrammatic form. But what we are looking at is about, just like Stewart said, deciding what you do in deciding what to model actually. So you are right. Yeah, I mean they may not agree with this approach, but
Are you going to interview anyway?
well, my area is that on the basis of the literature, I will review my methodology with the simulation people and how do they find that useful. I mean, of course, there are like in diverse people for software engineering, they may or may not agree. For example, Balsi or Arthur, I mean, they do agree some aspects that yes, it is a domain of what to model. But they say that no, it is a system description only. That's like Stewart said. So they mostly do the system description. Even if I do ask them, they will not change their opinion. So,
yeah, I've got a similar comment actually. So I teach software engineering, and I would have thought that normally use case diagrams are there for analyzing systems, very useful. And a graphical representation would be similar to a prototype in software engineering. And I didn't see those two things in your list. Is that not a good way of representing and linking what we do?
well, I did say the modeling languages. So it's a broad use case, UML, and flowcharts. And well, we did also try to attach use case scenarios with the preview because the original author did that. But yes, they do use that also for conceptual modeling, along with the ER models, which are entity relationship models. So ER models, UML, use case, all techniques there are there. So yeah.
I was a bit confused with your SADP. What are you trying to represent? Is it the activity in a model or the modeling activity?
It is basically an approach in the software engineering, which is a structured analysis approach. They start with the top level, right?
No,
They,
I get that one because I understand SADP. Just
what we are trying to do.
Yeah.
We basically converted it for a modeling purpose. So my SADT conceptual model does start from a single unit of activity. So each activity is the main unit.
Yeah. What kind of activity? It is the activity in the model, simulation model, or the modeling activity of a modeler.
No, it is the main activities that are there to be modeled in the final DAS or in the model. So those are the activities. That is why when we do abstraction, we cancel out from those activity lists. We can cancel out those irrelevant activities. And the framework, which is a complete framework, which may appear later in the paper or somewhere. But the major framework contains some steps which asks you to list down the activities and then relate all the components of the activities like controls and the resources, because we believe that activity is the main individual unit of DES modeling. So with each activity we can relate controls and resources, entities, and then we can come up with these individual modeling units.
Be careful who you talk to, because as I understand it from the discrete event simulation community, there some people they think event is the core, so that's why they have event and then program. When they do programming, when they implement the code, they use event handler. There are people who are really more on the activity centric. There are people that is more on the process centric. So
Yeah, I mean,
so
we did try with the queue, we did try with the activity, but basically the components, because there's, we didn't go into the detail of what the framework of this was, SADT, we just wanted to give a brief of, but actually it is a framework which lists down the system description in a format which is activity based.
I think the
the argument there would be that probably your typical clients would think about activity rather than event or process primarily. I mean, activity would be the core of, if we draw a process map, it's a process map of a series of activities that are undertaken.
One more question.
Just an observation. We've done quite a lot of work with system engineers to build models. The getting a shared understanding or getting appropriate abstraction and simplification always seems to be the most time-consuming and frustrating part trying to build these models. So I think it's quite interesting to see how you get on with the design.
Yeah, we are still looking for.